This conference will now be recorded.
Hello students, good every
This conference will now be recorded.
hello students, good evening. So today we'll be starting a new chapter, that is wave optics. So in the previous chapter we had learned ray optics. Okay, so what we have learned in that, we have seen that light as a ray. We have seen light as a ray, or light is a collection of rays or beams. Okay, light as a ray in this chapter. So when we considered light as ray, we have considered that light propagates in straight line. Okay, in straight line. But however, this wave optics was necessary
This conference will now be recorded.
Good evening students. Today we'll start with a new chapter, wave optics. So in the last chapter we have learned about ray optics. So in the ray optics we have considered light as a ray, or we can say as a beam, collection of ray. Okay, we have considered light as ray, and we have by default considered that light propagates in a straight line. Propagates in a straight line. So that is what we have learned, or we had considered about light. And with this, we could very well explain the phenomenon called reflection of light. So what is that? If you have a mirror, whether it is plane mirror or spherical, whatever it is, so light ray will come and reflect like this. Okay, so we had used bit of geometry, and then we had explained various phenomena in the nature. Okay, not only that, we have learned, or we had discussed refraction of light. With that also we could explain various phenomena like total indirect reflection, and there we had seen the mirrors, etc. We could explain well. But then why do we need this wave optics at all? Yes, here is the question: why do we need wave optics? See, whenever there is a new theory, it is not just for fun. It has come for explaining something which was not, like, suppose the ray optics, it was not sufficient to explain certain phenomenon. What are those? Like interference, diffraction, polarisation, etc. You might be thinking, what are those? let me tell you why do we need wave optics here. See, we have seen in the previous chapter ray optics that light travels or propagates in a straight line as ray like this. Okay, they cannot bend. But when light is passed through a sharp edge, look here. See, obviously when the wavelength of the, okay, so this concept was not there by that time. So when the light is passing at the edge of a sharp obstacle, then light gets bent like this. It is no longer straight line. See, light passed like this. See, light should have passed like this itself. Okay, but now light, see, you will see some light over here also, here also. So light gets bent. So this phenomena is called diffraction, which could not be explained with the ray optics, concept of ray optics. Okay, not only that, there is another phenomenon. See, we have seen superposition of waves. Okay, superposition of waves in sound waves or simply waves. Okay, so there we have seen when two waves are interfering, okay, or falling one on its on the other, falling one on the other, then some places there are maximum intensities or amplitude, somewhere amplitudes are minimum. So in this case also we see, in case of light also, if we have two lights interfering on each other, some places we see bright region, some places we see dark region. Like this alternate dark and brightness we can see. It is very, very surprising with this ray optics. We cannot explain why two light can give, or how two lights can give darkness when they interfere on each other or fall on each other. How can two lights gives darkness? It is actually here is the actual need for wave optics. Okay, then another phenomenon is like this. See, wave can be, like light can be confined in a plane. Confined in a plane. If you see, light is confined in, suppose in the xy plane. XY plane. If this is y vertical plane, let us say xy plane. See, the light is actually confined in the. In this case, it is. This is actually in the yz plane. Okay. It is confined in the yz plane. Here it is confined in the xz plane. Okay, so light, how come light is confined in a plane or oscillate, or it is in a certain, like localized in certain plane? Ray optics cannot explain this phenomenon. So these are known as, so the first one I showed you is called diffraction of light, where light gets bent. But in ray optics we have seen light can always travel in a straight line. Second thing we have seen is the interference, where two lights gives darkness upon falling on each other. So how come that happens? That cannot be explained by ray optics. And this third phenomena is called polarization. So this polarization, okay, this could be written as this also. So polarization, this is the confinement of light in a particular plane, or light is yeah, so that is, so these are the phenomena basically which could not be explained in terms of ray concept. Okay, or in the ray optics you cannot explain this phenomenon. So we'll be learning slowly that in the modern science or in the modern physics, we'll be learning that in this universe, any object in motion is associated with wave called matter wave. But here anyway, this light is not a matter wave, it is actually electromagnetic wave. So here we'll learn that this is light is electromagnetic wave. It consists of electric and magnetic field, okay, and they are oscillating in a direction perpendicular to the direction of propagation of the wave, okay. So like this, it is E, this is B. We have already discussed in the electromagnetic chapter what is called electromagnetic wave, and it does not require medium. But anyway, this wave theory or wave optics was like, it has a flow of development of this theory, wave theory. So in the very beginning, it was not so easy to accept this wave theory of light. We'll discuss what how it was progressed, like, okay. So what was the progress of this theory? So in the beginning, I'll tell you before I go into the matter or discussions, today's discussion. So today basically we'll be discussing Newton's corpuscular theory, then wavefront, Huygen's principle, and the introductory words of Huygen's wave theory. So in this chapter, we are going to learn wavefront, Huygen's principle, and how to use Huygen's principle to explain. Huygen's principle means this is actually related to wave theory, and Huygens is the first person who was dared to contradict Newton's corpuscular theory and put forward the wave theory of light. And then we'll move on to, okay, we'll just use this Huygens principle or wave theory to explain reflection, refraction phenomenon of light. See, whenever we have a better theory, you have to remember that better theory can be able to explain the phenomena which were being explained by ray optics, okay. So here wave theory is the better theory we are thinking. So wave theory should be able to explain this phenomena as well, okay. So here reflections, refractions of light could be explained with the wave theory, which we are going to discuss. Then superposition of light or interference, then related experiment, Young's double slit experiment, then diffraction, single slit diffraction will learn, and then finally we'll be learning polarization. Even though in some examination this polarization has been deleted from the syllabus, but still we'll just have a knowledge little bit, not very detailed, maybe introductory idea we'll have from polarization part as well. Okay, so let us start with our today's discussion, that is Newton's corpuscular theory, and then we'll see how slowly wave theory came and contradict corpuscular theory. See, Sir Isaac Newton, actually he proposed the corpuscular theory. This is kind of this is kind of supporting the wave theory or rectilinear motion of light itself, okay. So what was this corpuscular theory? According to Newton, every source of light emits or produces very tiny elastic massless, whereas that is rigid. Particles of different shapes and sizes. Okay, different shapes and sizes. Okay, so this was Newton's idea. So every source of light produces very tiny elastic massless rigid particles of different shapes and sizes. And he has proposed, I'll just write few points over here. So light consists of tiny particles called corpuscles. So these tiny particles are called corpuscles, and these corpuscles are shot out with very high speed from the luminous object. Okay, and these are actually elastic, massless, rigid, and depending upon the colors of light. See, we know by now that there are 7 colors: vibgeos, violet, indigo, blue, green, yellow, orange, red. So depending on the color, these corpuscles will be of different size and shapes. So this was Newton's idea about the light. So see, at the time he could think that these are corpuscles or tiny particles, and you know, in the classical limit, particle always moves in a straight line. Okay, moves in a straight line. So that was the idea. And here one more point. Okay, let us see the achievements of this corpuscular theory. So corpuscular theory could explain very well rectilinear motion of light, then phenomena of refraction, reflection, etc., and also dispersion. So those phenomena could be explained well. But one thing he had told, which is that the speed of light in the denser medium is greater than that of okay, so the speed of light in the denser medium is greater than that in the rarer medium. So how did he justify for that? He thought like these are tiny particles. So this is rare medium and this is denser medium. Okay, so he thought the denser medium will attract the this particle corpuscles of the light very faster or with a greater force, so that they will have greater speed than that in the rare medium. So this was the idea or the underlying concept of corpuscular theory proposed by Newton. This was proposed in 1670 7 AD. However, various phenomena of light were not being able to by corpuscular model or corpuscular theory, but because of the influence of Sir Isaac Newton's like by the time he was really famous and he had great contributions in the physics, mathematics. So because of his influence, he like this proposal or this theory, corpuscular theory, was not being discarded, even though it was not very successful to explain various phenomena with light. However, his contemporary was Dutch physicist Christian Huygens. You look here, 1678, he actually proposed that light cannot be a particle or a ray. Light is a mechanical wave. What he said, Dutch physicist Christian Huygens proposed that light is a mechanical wave. Mechanical wave means, you know, it requires medium, right, for propagation. So people asked question about his concept that light is a longitudinal and mechanical wave. So when this question was put forward, he just thought, or he had given answer in this way, that light propagates through an all-pervading hypothetical medium called ether, luminiferous ether. And this ether medium, see, we know the speed of light is so high, and see, wave, basically the sound wave speed is actually classically elastic constant or elasticity divided by density, right? Kind of this. Mechanical wave has velocity similar to this, okay? Not only sound wave, even any mechanical wave will be having this classical idea that square root of elastic constant divided by density. So he speculated that this hypothetical medium called ether, ether, luminiferous ether is all pervading, okay? It is all pervading, between like all pervading, and this medium has certain qualities like high elasticity, and then it is having very low density, very low density. That means very dilute and spread everywhere. Okay, so he had answered in this way that, or he proposed that light is a mechanical wave, longitudinal mechanical wave, just like sound waves, and it propagates through all pervading luminiferous ether medium, and ether is very highly elastic and very dilute or low density and all pervading medium. But however, after some time, this idea about longitudinal wave was eradicated by that was eradicated by Young. Okay, so light is not longitudinal wave. This was actually proved by Young from various experiment. He proved that it is not longitudinal wave. So Young said it is transverse wave. Transverse wave. Okay. So this proposal of this presence of ether medium was again opposed by the Michelson-Morley experiment. As you might be learning, Michelson-Morley experiment has actually proved that there is no such medium called ether. Okay. Further, Huygen said that light is a mechanical wave, but see, by the time Maxwell actually developed EM theory, electromagnetic theory, where he could explain that electromagnetic wave, when travels in vacuum, its speed is something which is nearly equal to the speed of light itself. Okay, speed of light itself. So then it was proved that light is also an electromagnetic wave, and which does not require any medium to travel. So thus the wave theory was, with various corrections, it was established that light is a wave. Light is a wave. It is not a particle so far, at least not the classical particle. Okay, so even though there are lots of faults in the proposal of Huygens, but it was accepted because it could explain the phenomenon called interference, diffraction, polarisation. Not only that, even the reflection of light also could be explained with the wave theory of light. Okay, so this is about brief history about wave theory, how it came and all. Now we'll just take that the light is an electromagnetic wave. So now, by the grace of quantum mechanics and modern physics, we know that light is an electromagnetic wave, and it has both particle and wave nature. So the latest theory is that light has two aspects: particle aspects as well as wave aspect. Okay, so in some cases, some phenomena, natural phenomena like scattering and Compton effect, like Compton scattering and photoelectric effect. So those effects, those effects are being explained by the particle aspect of light, quantum particle, obviously not the classical particle. So which are a pocket of energy. Okay, energy pockets. or pockets of energy, h nu. Okay, energy pocket or quantum particles. These are called quanta. Okay, quantum of light. Okay, in known language, energy pockets. Okay, and wave theory, which we are going to learn now. Okay, let us go ahead. So first we'll learn what is wavefront. Okay, if I say what is definition, what is the definition of this wavefront? Wavefront is defined as a continuous locus of particles of the medium which vibrate in the same phase at any instant. It is very difficult to understand. Same phase, vibration, etc. So we have learned already mechanical wave, right? Like transverse wave, longitudinal wave. Transverse waves propagates like this. Like if it is propagating like this, the medium will be just a string. You know, string, if you just plug in the middle somewhere, okay, middle or somewhere when the other ends are fixed, so it will actually produce a transverse wave. So wave propagates like this, but the medium particle will be oscillating like this. Okay, so what is phase and all this we have already discussed in the 11th standard, but what I'm trying to say here is, see, wavefronts are actually locus of continuous locus of those particles in the medium which are vibrating together. See, if I give you a simple example, suppose you have gone for a music and dance program, and you see in the dance program, in a group dance, obviously, so there are 8 artists, 8 dancers. So 4 among them are dancing in a particular pattern, and other 4 they are dancing together in some other pattern. Okay, so the 4 which are having equal pattern or same pattern are called moving in a phase. Okay, so I'll repeat it. Suppose there are 8 dancers, so they are doing group dance. 4 among them doing some pattern, dancing some pattern. Sorry. They're dancing at some pattern, and 4 other 4s are doing some other pattern. Okay, they're moving in some other way. Okay, they're stretching or bending or doing various mudras in different patterns. Okay, so these 4 will say they are moving in a phase, in some phase, and these 4 people are also, they are moving in phase separately. So these are in phase. These 4 people are dancing in phase, and these 4 people are also dancing in phase. But when we say one among them and one among these, okay, so one among these, if we take, they are actually not moving in a or not dancing in the same pattern, so these are out of phase. Okay, out of phase. You take someone, maybe someone from here and see someone from here, they are not moving in the same pattern or they are not dancing in the same pattern, so they are moving out of phase. Okay, so this is the concept of in phase and out phase. So what is wavefront? I'll explain with another simple example. This might be familiar to you. Look, suppose you are standing on the bank or shore of some pond, and you are just dropping a stone, small piece of stone on the still water. So how does that look? So there will be some circular patterns emanating from the point of impact, and those patterns will be moving away, right? And see, in those patterns what actually happens, you know, so there will be some disturbance created at this point of impact, and waves will be generated from here and propagating all the way up to the shore, or up to the is up to the shore. So in this, you look, some of the water particles, they will be moving upwards. See, these are, see, they are moving upward. So the water particles here, they are all moving upwards together, okay, on this circle. In a particular circle, if I take, so all the particles, they are moving together in the upward direction. And if I take some particle in this depressed region, okay, this is actually depressed, right? This is elevated region, this is depressed region. You can see this also, this is depressed region. Okay, I'll just clean everything. See, this is elevated region, this one is elevated region, and the circle I have made here is also elevated. This is called actually crest. So you look, all the particles on this circle are moving upwards together, or vibrating upwards together, and the particles over here, they are also moving in the downward direction together. So all the particles on this circle are moving in phase. So if I just draw a line like this circle, okay, this will be a locus of all the points. So this will give a pattern, okay, or a particular shape which is called wavefront. Okay, so when wave is generated from particular source, and that disturbance, actually wave means disturbance, as you have learned, so that disturbance will be propagating through the medium, right? So this is, I'm talking about mechanical wave anyway, but Huygen's principle, as he had thought that there will be some medium, we will obviously take for the time being that light wave has also certain pattern, okay, certain shape while propagating, okay, or from the particular source. Look, these wavefronts are actually surface with constant phase, and speed of these wavefronts are the speed of light wave, okay, speed of light. The speed of the wavefronts are of speed of light, okay. Here it is actually, if I say this is light wave, if it is sound wave, then maybe we can say that is the speed of, like, see, wavefront can be created by mechanical as well as this electromagnetic wave. Here we are learning at least for the light, okay. So there are different types of wavefronts. See, when the source is a point source like a bulb, okay, bulb will be actually emanating light in all direction symmetrically, isn't it? So light wave, if I just draw a sphere keeping this source of light, as you see here, keeping the source of light in the middle, then we can have various concentric spheres or spherical surfaces. So those surfaces are actually wavefronts, because see, at each point you look this on the surface of this sphere, each point is actually equidistant. Okay, that means all the points like this point and this point, everywhere the light takes the same time to reach. Okay, on this surface, so they are in phase. Similarly, if I just consider this one, this spherical surface, so this spherical surface is also a constant, like surface of constant phase. So these are spherical wavefront. So spherical wavefront is produced by a point source, when the source is a point source. Okay, point source. Now when the source is like a tube light, a linear source, then we see cylindrical wavefront. Okay, wavefront just by the symmetry of the source of light. So wavefront will have the shape according to the symmetry of the source from where the wave is emanating, like a rectangular slits like this. Rectangular slits will actually produce cylindrical wavefront. Okay, cylindrical wavefront. All right. Now this spherical wavefronts and cylindrical wavefronts, when we see this, see if these sources are very far away from the observer, then at very large distance we will see part of this. Okay, part of this spherical surface or cylindrical surface. Then how we look them as plane. So when this spherical wavefronts or cylindrical wavefronts travel a large distance, they become plane wavefront. Or in the other word, if we see them from very far, then we see a very small part, tiny part of that, and that becomes plane wavefront. Okay, so these three types of wavefronts we see. Now if we draw perpendicular to this wavefronts, look here, these are actually rays. Okay, outward, obviously along the direction of the propagation of wavefront. If we draw perpendicular arrows, so those will actually represent the rays of the light. Okay, and a bunch of rays are called, is called beam of light. Okay, so many rays together, it's called beam of light. Okay, together it's called beam of light. All right, now we'll just go to the Huygen's principle. So according to Huygen's principle, each point, see, we have seen here, so we have obtained these wavefronts by connecting all the particles which are vibrating in same phase, right? We connect them and then get the surface. See, on the wavefront, each point, according to Huygens, on the wavefront, each point will act as source of secondary source of light. Okay, according to Huygens principle, each point on wavefront will act as source of secondary waves. Okay, or these sources are also called secondary sources. Okay, so and the waves which are created by, see, waves may be created by this point, so wave will be created by this point. Okay, these are called wavelets. That means secondary waves together, many waves together called wavelets, and the source is called source of secondary waves. So each point on the wavefront will act as source of light, and each source will produce waves of light, and those waves are called secondary waves. So According to Huygen's principle, each point on wavefront acts as a source of secondary waves which add up to give a wavefront at the later time. So as I was showing you, suppose here this point produces wave, this point produces a wave, okay, this point also produces a wave, point propagates, these waves all add up and give, see at this point, if we just connect these points where they are impacting and the medium is vibrating in phase, if we connect them, they will give the wavefront at later time. It takes some time to go from here to here, right? So at later time, those waves are so the sources, so which add up to give a wavefront of at the later time. Okay, all right. See, Huygen's principle actually a geometrical construction. Will just show you how is it. Before that, let me tell you few assumptions that those were made by Huygens. First one is that each point on the wavefront acts as fresh source of new disturbance called secondary source. Then secondary wavelets spread out in all directions. See, point means each point source, they will act as point source. So they will actually produce waves in all directions, okay, like this. And these waves will be spreading out in all directions with the speed of light. In particular given medium, speed of light in the vacuum is c, but in medium it is different. And the new wavefront at later time is given by the forward envelope of secondary wavelets at that time. I'll explain this. Look at this particular point. Okay, the new wavefront at later time is given by the forward envelope of the wavelets at that time. Okay, so now we'll discuss about the Huygens principle or the geometrical constructions that Huygen used to explain how to get new wavefront. So Huygens principle, as I said, it is a geometrical method of getting or locating the new position and shape to get the new locations and shape of the wavefront. That is in very simple language at any instant like say at later time. Okay, at later time you have to have again the wavefront, right? But how to locate it? How to locate the position of the wavefront and shape of the wavefront? How to get the shape of the wavefront? That was suggested by Huygens principle, and it is actually nothing but a geometrical construction. See here in this figure, see I say there is a plane wave. Plane wave can be represented by a straight line. Here, see AB is a plane wavefront. Okay, plane wavefront. AB, you can see AB. This line is a plane wavefront, and see I have taken A, B, C, D, E different points. Okay, on the wavefront. So what they will do? They will produce secondary waves, right? So these wavelets will move with speed c. Okay, so from each of them the waves will be produced and they will move forward like in all direction it is said, but always wavefront will be taken as the forward envelope or tangent to the surface we get. Okay, like tangent to the here I'll just tell you here, see this is the point A which produces a wave which is moving forward, okay, forward direction. And suppose after some time delta t it meets here, okay, at this particular position. Okay, so this, see, this is actually going all the directions, right? All direction like this. So I have kind of semi sphere, like a hemisphere shape, kind of this. Okay, hemisphere surface. Okay, so after some time, see, after some time it will actually reach at this particular distance c delta t. Okay, from here also it will reach here. Here also it will reach here. So you can see this hemispherical surfaces here, and if you just take the tangent at each of them, then you get a plane surface, you get a surface. Okay, if this is a spherical surface, if it's three-dimensional spherical surface like this, if you take a tangent, you should not have a line, it will be actually surface. So this actually going to give the new location after delta t time. It is going to give the shape of a location. Anyway, you will get here, here, etc., but you will get the shape of the wavefront, new wavefront here. Okay, so you are taking here the forward envelope, look, or tangent in the forward direction. Okay, in the forward envelope you are taking, or the tangential surface CD we are taking here. So this is a prime b prime. So tangential surface a prime b prime after delta t time. Why don't we take this a double prime and b double prime in the backward direction? Why we are taking forward envelope? This is, this can be explained that, see, we have seen, or it can be shown mathematically, that the amplitude of the secondary wavelets is proportional to 1 plus cos of theta. Okay, now see, this theta is the angle between the ray, okay, and the direction and the direction. So this is the angle between the ray at the point of concentration, okay, and the direction of the secondary waves. Secondary wave, suppose it is moving in this direction, and we are just taking the ray in this direction. Okay, so the angle will be, I'm sorry, we are taking the point. The ray will be taken in the direction of propagation of wave itself, but we are just taking that wave is not propagating in the opposite direction. That is what we are thinking. So ray is taken this direction, but I am considering the point over here. Okay, so the angle is pi. So pi will give you -1 here. So -1 it will give you 0. I'll explain once again what it is. See, we have taken the new wavefront as the forward envelope. Okay, forward envelope. We are thinking that wave is not propagating in the backward direction, but it is not possible, right? It is not possible. But anyway, the amplitude of the secondary wavelets depends on this factor. Okay, it is proportional to this factor. What is this angle? This angle is the angle between the direction of ray and the point. Suppose if I say this point here, this point, whether the, like, what is the amplitude of this secondary waves at this particular position? So it has certain angle, suppose. Okay, so I'll put it here and get the amplitude here. When I have the point here, so what is theta? This theta is pi. Okay, with respect to this direction of propagation of the wavefront, okay, or the ray. So here pi means the total amplitude will be 0 in the backward direction. Okay, so amplitude of backward, amplitude of the secondary waves in the backward direction would be 0. Okay, so they'll cancel each other. That is what it is said. Okay. Now this can be seen like this construction, geometrical construction. This is the plane wavefront. This can be shown with spherical wavefront as well. Okay, suppose at certain instant of time, a part of spherical wavefront is this one, A, B. And similar way, we take the points A, B, C, D, E, etc. So these points will act as secondary source of wave, like light. And from here, secondary wavelets will be emanating and moving in the forward direction, as I said. And certain instant of time, like delta t, after delta t interval, you will be able to find out the position and the set. Position is here anyway. Okay, you will get, because this is a straight line distance from this center to this center. Okay, and this wavefront will be kind of a spherical surface. So you have to, if you just draw a common tangent to all of them, all the spherical surfaces, okay, spherical surfaces, you will see, you'll get this tangent also will be a spherical surface. So this is how Huygen's principle or Huygen's geometrical construction actually gives you the position as well as the shape of the new wavefront you get after certain instant of time. Okay, so I'll stop it here for today. In the next class, we'll be using Huygen's principle to, we'll apply Huygen's principle to explain the reflection and refraction phenomena of light. Sorry. Okay, in the next class. Okay, so thank you for your patience. Bye for today.